Welcome to Study Loop.
Here we are looking at the dissociation of F2 in the gas phase to form two individual F atoms in the gas phase. The first question is whether this is an endothermic or an exothermic process. You could go to your appendix and use delta H values to calculate it that way, but here's another way to think about it. F2 is one of the molecules that exists in the diatomic state. F2, Br2, Cl2, I2. All of these halogens prefer to exist as pairs rather than by themselves. Since this is their natural state, you have to put in energy, or heat, if you want to break them up into separate atoms. So you could think about this as heat plus F2 is in equilibrium with 2F. An endothermic reaction is one where you can think about heat as a starting material, while an exothermic reaction would be what we had if heat was a product instead. Once again, this is because you have to put energy in to break up F2 since that is its most stable and preferred state. Next, if we increase temperature, how does that impact the rate constant? Well, if we increase temperature, that's like we have more of this starting heat. And we would then be able to form more of F. Therefore, if we increase temperature, we will put positive pressure on the system to shift towards the products, and at equilibrium we would have more of our F as opposed to our F2. So K would increase. That is generally true for endothermic reactions when you increase temperature. Finally, if we increase temperature, how does K of formation versus K of the reverse reaction? In other words, will Kf be larger compared to Kr? Will it increase by a greater amount, or will it increase by a lesser amount? Well, remember that the equilibrium constant is a ratio of the forward reaction over the reverse reaction. So if K itself is going to increase, then we're going to need little kF to increase by more than Kr, because overall big K has to increase. Therefore, Kf increases more than Kr.